First of all, thanks for the invitation. I appreciate it. My name is Lee Johnson, N4WYE, and I'm in the North Fulton Club. And this is a presentation on antenna modeling. I started doing it about... The microphone's working, isn't it? It's on. Hello, hello, hello. Okay, is that better? All right, I'll hold it up a little bit closer. All right. Can you hear me all right now? All right, fine. I got back into ham radio about 3 years ago. Started out my ham radio life in Hawaii in 1957. And for those of you who are old enough in the room to remember, that was Sunspot Cycle 19. And it didn't get much, it hadn't been gotten much better than that. So it was a good place to start my ham career in Hawaii with a novice license. I'm also a founding member of the Raleigh Amateur Radio Club, and we started in the late 60s. I built the original 0464 machine in Raleigh, and I don't think it's still in service, but the frequency is still used. And that was, I worked for ITT at the time. They had a Mackey Marine radio division. Some of you may have heard of that. They built shipboard radios for commercial shipping. And so they had a VHF transceiver project that was being built for the ships. And I took parts off that and built the 0464 machine. I retired from the high-tech world I was in there about 40 years, I guess. And I'm a North Fulton Amateur Radio League member. And let's see. Make sure I got the right button here. On this modeling program, I'd like to take you through a couple of steps. One is, what is it, and why would you want to use it? And is it really difficult? A lot of us have. I just did the Nano VNA presentations, and a lot of people felt like over the last few years that Nano VNAs were too complicated, and I think people have kind of gotten used to that idea. And modeling is the same way. It's not that complicated if you have the right starting point and you have some sense of how to get it done. There's enough YouTube videos out there, it helps a lot. So I started putting up antennas about 4 years ago with a dipole, went to an off-center fed dipole, went through the end-fed, crossed end-feds, and then I got into the loops, and I really liked the loops a lot. And I wished I had known what I have figured out between all those antennas and about modeling when I started the process. I learned about modeling as I was finishing the process. But in any case, I'll try to give you some examples. Some of you have probably expected to see EasyNIC listed up here. We'll talk about that a little bit later on. And I'll let you know why I decided to go with MMANA instead. The basic idea, by the way, with MMANA, it uses the same basic mini-NIC engine, but it has a graphical user interface. So you don't need to work in X, Y, and Z coordinates exactly. So that's why I started using it. And the only problem apparently with MMANA not being quite as good as EasyNIC is that if you're within 2 or 3 feet of the ground, it doesn't do a good job of modeling that. Well, I wasn't worried about that problem. And what I'll try to do is I'll try to go through with you what MMANA is like, how it operates. I'll do a demonstration video on actually modeling an antenna and walk you through it. And then also how to get MMANA, which is free, by the way. And also give you some references on YouTube and things like that. Most of you know Callum M0. He's the DX Commander guy. He's got some videos out. He's got some really good videos on how to model with this, and that's kind of how I got started a couple years ago. So we'll get going here. Where did modeling come from? Where did it get started? And what's a little history behind it? The Navy was doing some work. If you look at the upper right-hand corner, that's a curved tower. so they can actually put an equidistant transceiver sensing units over a unit to be modeled. They were modeling ships, and so they had a pretty good size range, and most modeling that was done with those kinds of antennas and everything that goes along with it are pretty expensive. So they've moved away from that and gotten into actually building the software to simulate that, to emulate that. And so we'll go through a little bit about that. It was done at Livermore Labs in California in the 70s, and that's the from the NEC, and that's the EasyNIC route. That's where it came from. Since then, the 70s, you've gotten away from batch machines with cards. You've gone to, computers that you can have at your desk, and the software is available. And EasyNIC 7, I think it's version 7. Current version. That one's free now, as of about 6 months ago, I think. And MMANA is also free, so you don't have to worry about paying for them. And more and more people are getting into modeling because with that software and a graphical user interface, it's an easy thing to do. And I'll get into showing you why you might want to think about doing it and try to convince you to give it a try. Here's a kind of a domain of modeling in a step back and look at it from a global sense. If you look at the upper left-hand corner here, this part up here and this part up here, that's what they started with, was modeling antennas on ships to make sure they had good propagation off the ships and they knew where the antennas needed to go and what kind of interference they were going to have from all the metal. Okay, and this is a chart that goes through a lot of different kinds of models. This is a method of moments method where they actually take and solve Maxwell's equations along the point of the antenna at thousands of points to be able to recreate and look for what's the propagation pattern going to look like. So you're actually solving Maxwell's equations. And for those of you who know what that is, God bless you. I went through that in school. I'm a double E, and I wanted to get as far away from those things as I could. The point is, they needed pretty good sized computers early on to do this work. Here's an example of a model that they're starting to work on now, which is what happens to the brain with a cell phone. So they're doing modeling of that now. So the modeling gets into even human tissue now. So they've gone a long way in a lot of different dimensions on modeling. So this one's a pretty simple one, what we're going to talk about today compared to that. Okay, here's Maxwell's equations, and this is the easy form of those equations. But the basic idea is that Maxwell, and by the way, the guy did this work during the Civil War. Okay, and the interesting thing about Maxwell is that he took electromagnetic waves and modeled what those things did, how they worked, how they interacted, and how they propagate. And Einstein was making a speech one time, and it was an honorary speech of some sort. And somebody asked him the question, do you stand on the shoulders of Newton? And he said, no, I stand on the shoulders of Maxwell. So Einstein took a lot of his work from what Maxwell laid out. So it's really an amazing set of mathematical computations to get to how do you propagate RF on an antenna. Here's the NEC original program. The free one right now, it's EasyNIC 2 version 7 is the one that's free. Okay, and that came out of the labs. There's the websites for them. Here's the licensed version of it. And here's the MMANA program. And there's two versions of that. This one's free, and that one's you have to pay for it. And the primary difference is the level of precision. Instead of, I think it's 1,000 points along the wire, you can do like, I want to say 40,000. The difference is the level of detail that you can get with the modeling. Yeah. These will be on the website as far as I know, right? You're going to put these up on the website? And there's some more references in the back in terms of, where to go get modeling stuff, where to get the software, and where to get some YouTube videos to go through it a little bit better. Okay. You might ask, why do I want to model an antenna? Well, one of the things I found out about putting up antennas in an HOA with a backyard that backed up to a street and big, tall oak trees, I had certain trees I could work with, and my house faces due north on the backside, so that was an easy starting point. But as I started looking at the propagation patterns of some of the antennas I had put up, I wasn't doing a good job down in Florida. So I started moving my infeds around and started to look at where I wasn't getting signal on some of the bands. And it would have been a lot easier to do it this way instead of put the antenna up and see if it works and then take it back down again and move it around. So the nice thing about it is you can model the antenna in 5 minutes. You can't get the box of stuff in the backyard in 5 minutes. So it's a whole lot easier to do it this way. And I'm here to try to share with you an easy way to do it. I did some pattern radiation plotting on my antennas that were up, with some of the tools you can get on propagation, and some of the software that they've got now that you can get, put a CW signal out and it'll give you a response back as to what the signal level was at some future point. I forget what they call that. Anyway, I was doing some of that to try to figure out what my patterns looked like. And it was this exhausting amount of time it took to try to figure out where was that antenna put in RF. The models tell you a lot about efficiency, pattern, gain, and input impedance. It's quick. You can model. You can iterate models easily. They're not hard to build. The interesting thing is, if properly done, they're very accurate. On the other hand, garbage in, garbage out. So for what it's worth, modeling can give you some crazy answers sometimes. And if you don't have a sense of, am I starting from scratch or am I just changing a model I've already done a little bit to point in a different direction? That's a lot easier thing to know if you're right or not. Okay, so modeling can give you garbage, but it can also save you an awful lot of time. Okay. Here's the MMANA. These guys did it in Europe. It's, let's see, in the late 90s and early 2000 time frame. So it's a much newer program than EasyNIC is. And let's see here. Here's the pro version. That's, I think, 45,000 points. I can't read it. Can we tune the focus up a little bit? Because it should do a better job than that. And we may need it later. Yeah, that's better. Okay, yeah, that's 45,000. Yeah, all right. Anyway, I won't get into that. I don't need to. Okay, this is my house, top-down view, Google Earth, and my antennas. And this lot is 1/3 of an acre, and I've got an 80-meter loop, a 40-meter loop, and an infed half-wave at 40. I'm going to turn this vertical and do an inverted L off that big oak tree. But I'm not so sure which way to turn the L part. So I'm going to do some modeling on that to try to figure out how to get my propagation the way I want to with that. But that's what my antenna farm looks like. The 40-meter loop is at 70 feet. The 80-meter loop, I could only get it up to 40 feet, and it took me 3 days to do that. But it works out pretty well. Okay, here's the set of pages that you go through to build a model, what the sheet looks like, what the different parts of the program take you through. But as an example, here's the SWR curve. So it'll draw the SWR curve for you, or tell you if you're out of the band or something. Okay. This is the input page here, and basically step through frequencies, and then you go through and you get all the data out in terms of SWR, gain, front to back ratios, things like that. And you describe it. You actually draw it. You can draw it in a graphical user interface. It's pretty easy to draw, and that's a 40-meter delta loop. And the real question was, what's the propagation of a 40-meter loop look like? Not just at 40, but also at 20 and 15 and 10. And what happened for me, before I did the modeling, I built this antenna, and when I put it up, I had a 60-degree angle on every angle. I had it up 70 feet, and I thought, now, I can only feed it from the one tree that I've got, because that's the shortest piece of coax I've got, the longest piece of coax, I'm sorry. And it was a Sunday afternoon, and it was like either I hook it up to this corner or I wait till Monday to work on one of the other corners. So I hooked it up. Turns out, if you look at this is the pattern of that antenna, and that's Europe. And it turns out, I happened to put it upright without knowing it. But I've gone back and modeled it, and this gives you an idea of this is a top-down view of what the azimuth looks like. And this is 0, -3, -10. So it gives you an idea of relative signal strength and gain you've got in which direction. It'll show you how much gain you've got with this antenna. This is about, I think, 6.5 dBi, which is about 4.25 dB gain off the main lobe here. So that's 4.25 gain. A dipole would be about 3 dB. So it's a little bit of a gain. Yeah? Yes, we'll go into that in more detail. And this is taking it and looking at it as a cross-section the other way. Okay, so you can get an idea of what the radiation, what the slope of the radiation is going to be. And there's the 3D model of it, and you can rotate this around and get some idea of what you're working with. So that's a modeled that I did, and you could probably do a model like that in half an hour, something like that. It doesn't take a long time to do it. That's not the first one, though. Okay. This one is on 20 meters. You'll notice that if you look at this pattern from 20 and 40, it's got a similar shape to it. Not exactly the same, but a similar shape to it. And you got a much better feel for what the radiation looks like. And it's kind of spiked up like that, but you'd expect that at a harmonic. But the basic idea was it's pointed in the same direction if you go from 20 and 40. So you can start to get a sense of, okay, which way do I want to point this thing? Where do I want to get coverage? Here's another way to look at modeling. Take an off-center fed dipole as an example. And let's say your yard's not big enough to put up an 80-meter in wire. You can't get 80 meters horizontal dipole up. What happens if you drop the ends of it to fit in a, let's say, less than 100-foot wide space? So you drop 13 feet off each end of that wire. If you look at the patterns, you don't see much difference, okay? This is at 80 meters. This is at 40 meters. And this is at 20 meters. Patterns aren't that much different. Okay? And you just took 25, almost 30 feet off the antenna. And so I modeled that because one of the guys in the club said, I don't have a lot big enough to do it. What happens if? And we said, okay, not much. Kind of surprised me. The other thing is, let's say you wanted to point this in a different direction. Well, if you take, instead of making a straight dipole, and you bend it at 135 degrees instead of 180 degrees, then you can just you can shift the pattern around to point in a slightly different direction. So it depends on what your trees are, what your supports are, and which way you want to go. So you've got some maneuvering room, and you can say, well, I can't use that tree, but I can use that one. You can put that in the model and get an idea of what's going to happen to your propagation pattern. And by the way, it really does work. Okay, here's an example of, I guess I squeezed it down a little bit. This is an azimuthal map. I'm not sure I pronounced it correct. But basically, I put my antenna propagation pattern on top of my house on a map that says, all right, what is the azimuth to that location? Okay. And you can get this off the internet. This guy did a really nice job. You just put your location, it'll put you in the middle, and you can start to look and see what azimuth you need to point your beam at. It's a nice map for that. But if you look at the propagation pattern here, this is an end-fed half wave, and this red line right here is, I'm sorry, let me get it right in a minute. Yeah, this is 40 meters. This red line is 20 meters, and the green line is 10 meters. Nope, that's not right. That's a 40 meter. I got 15 on there too. I've lost track of which one's which because there's only 3 of them plotted. But anyway, it gives you a sense of what's the pattern look like on a multi-band antenna. Yes, sir. 66 feet. Yeah, that's, I'm sorry. I have both end-feds that I've worked with. That's a 40-meter end-fed. And but anyway, you can, I still can't read that, but and I've lost track of which one it is. But the what you find is you end up with on the fundamental frequency you're operating on, it's a pretty benign sort of pattern, as you might expect, and you get multiple lobes on it as you go up in frequency. So this circle here is the 40-meter pattern, and the next one is this pattern. Okay, that's a 20-meter, and the red one is the I don't know if that's 10 or 15. I've lost track. I just want to give you a sense of how to lay it out and take the model results and put it on a map and say, okay, where's this propagation going to go? Okay, with the modeling, basically you describe the antenna. This isn't a design program, by the way. This is a program to evaluate. Okay, you're the designer. This won't build an antenna for you. It'll tell you what the antenna you'd like to try will do. So this is what you put into it in the program. And then the program itself will give you the pattern gain, front to back ratio, source impedance SWR, and what the currents look like in the antenna. Yes, sir. Dropping the ends down, leaving the conductor the same length. Right. Just dropping the ends off. Okay. So it's a shorter conductor that's horizontal, and you got 2 vertical pieces on the end of it. Okay. But I was assuming that you wouldn't be putting an antenna only 13 feet above ground. You'd probably put it a lot higher than that. Okay. The basic procedure on running through the model is you start with the geometry tab, which was one of the 4 tabs I showed you earlier, and we'll go back into it in some detail. And you name the antenna, and you plug in what frequency you want to start with, what the fundamental frequency is for, let's say, a multi-band antenna. And then you take the wire edit and start drawing the wires out, and it's basically just a graphical user interface, X, Y, and Z coordinates, and you can lay it out with a mouse. Close that, and then make sure that you feed it with something. You put a source sources, the coax going in or whatever you're going to feed it with. And then you go to the Calculate tab, and you set up then what the ground looks like, and you can do that in a fair amount of detail. And we'll show that in a minute. And you look at what material, you're using copper wire or you're using something else, and then what the height is, hit the start button, and it'll do the model. And then basically you can look at the plots and iterate on what the plots look like. You can also do an optimization. I mean, let's say you built a beam and you wanted to optimize it for, let's say, front to back ratio. You can choose that as a parameter that you want to rate highly and try to convolute on. Or you can it's a subset of the program that will allow you to optimize probably about 6 parameters, all the way from front to back ratio, gain, impedance, SWR, and a few others. Okay. So you don't have to sit there and cut and paste and go at it that way. You can actually just let the optimizer do it for you. Okay. We're going to model an antenna. All right. And we have already left the geometry page because all we put on that page was the name of the model for the file name and what the fundamental frequency is. And we're on the second step now, which is we've gone to the view chart and we're going to actually draw it in. And I'm just going to run a short video here to show you what that process looks like. In 8 seconds that dot doesn't move, then there we go. There's the geometry tab. So we go back in there, put the name in there. I just thought we'd stick with a dipole and keep it simple because we know what to expect. And you saw you can pick out what frequency you want, and most of the bands are marked in there, so it's easy to, you don't have to type it in. Okay? And we went to the second step. And here's the graphical user interface, new wire. And this is in the ZX plane. So I'm just drawing a dipole. And you see it shows what the length is right up here. The length of that 21 meters. By the way, one problem is it's in meters, not feet, so you have to bear with that a little bit. Okay, there's the first page, and it just populated that matrix for you with what you drew. All right, so now we're going to go back and look at, all right, let's finish the input. What kind of ground you got? Free space, perfect ground, or real ground? If you go to ground setup, you can go into a lot of detail on how you want to populate that. You want to use salt water, you want to use the average number. Most people use the average number and don't spend too much time on it. This is also where you put in your radials for your verticals. Okay, you can define the radials and put them in there. We're not going to do that this time, but that's what you do there. Here's the height above ground, and I put 20 meters, that's 65 feet or so. And then copper wire. So now you've kind of said, okay, what's this antenna look like? How far above ground is it? So it's a half-wave dipole on 40 meters at 66 feet. Okay, now, add a source. There's a round red circle right there. Okay, and it's the 50 ohm. It assumes you're starting with a 50 ohm impedance. You can change that, like if you have a balun or something like that. So here we go. We're ready to go, and there's a start button down there someplace. What are we missing? Oh well. Oh, there's a bandwidth that I picked. You want more than 40 kilohertz. So 6.9 to 7 point almost 4. You speculate on what the SWR is going to be. Or you can do a detail run of it, and which is the number of plots. And so you see, you're below 2 to 1 that part. And I didn't optimize it to move it up. I just left it here for the model of this one. And it'll keep stepping through the model and show you the rest of it as we go along. But there's a starting point. You know you got the length about right. So you're in the ballpark. All right, and here are the steps. There's the impedance, complex impedance, SWR, and all the details of it. And you can see the details written up there. And now you can look at the far field plots. And that's kind of what you'd expect the dipole to look like. Okay, and you see the gain up there is 5 dB. dBi, so you got to take about two and a quarter off that for a dipole. And so it comes in a little bit. And that's what the radiation angle looks like. And then you can take a look at, see, it'll actually show you the radiation angle and give you a sense of, you know, how low on the horizon is the propagation going to be. And then you can look at the 3D. I'm not sure why the bottom of that's cut off. You got any ideas? Oh, okay. Okay. There's a 3D model. You can rotate a little bit and get some idea. And the darker the color, the more gain you've got in that direction.
How do you do things like NFEDs and stuff that have some sort of trope or transformer or a matching network at the base?
It's actually relatively simple. An NFED is about 2,800 ohms impedance, actual impedance on the end of the wire. So you just, instead of 50 ohms, you put 2,800 ohms in there. It takes care of it. Some magic. And if you want like a 4-to-1 balun, just put 200 in there instead of 50. So it's a relatively straightforward thing to do if you know where to go in the model. Okay. Okay, here's a couple of good things to think about as you're modeling. A good starting point with modeling is take somebody else's model and use it to your advantage until you start to learn the process. And with MMANA, there are tons of files of all different kinds of antennas in files already that you can start with. So you don't have to start from scratch. You know, and they've got probably, let's say, 2,000 or 3,000 models already in the file, in the library. And basically, you can look at the beams if you want to play with beams, kind of learn that sphere of parameters to deal with. And what you'll find is you'll get used to what to expect because you kind of know what a dipole does at different heights. So if you look at a model and, you know, and the results don't look like this, what they should, it won't be just a little bit off, it'll be a lot off. So it'll be obvious in many cases. So small changes won't change the performance a lot, but you'll know you're still on the right track if you don't do something crazy. Like for instance, just one second, let me finish the sentence. I had modeled a loop and I had forgotten to change the 50 ohms to 200 ohms. And the SWR curve looked crazy. And I thought, well, and I couldn't get it to close. It was resonant 3 megahertz off where it's supposed to be. And sure enough, I just had made a mistake and I had to go back and finish putting my input in. But there's a small list of the libraries, but it's 3 or 4 levels deep in terms of indentation. I'm sorry, my apologies.
Well, I was curious. I've played in school a little bit with NEC. I know that curve shapes like loops are more difficult because you've got to take a bunch of straight lines and pair them up. Is there an easier way in this software to do a loop as far as choosing your side, or do you have to still detail out each straight line and make a loop?
When you say a loop, do you mean a round loop?
Yep.
Okay, I thought you might. The answer is, I don't know, I haven't done that yet, but I suspect that you might have to do some segmentation. You know, maybe have 16 or 32 segments on it to get it right, but I don't know for sure. But the good news is you can always make it, more precise by making more segments. One of the things that I have found out about MMANA, it solves some of the problems I had with EasyNIC, where if you were modeling, let's say, a dipole, instead of putting 2 wires in a feed point, you needed to put a short wire in the middle with the coax coming into it before you attach it to the feed point. You don't have to do that with MMANA. So little things like that have kind of been gotten out of the way. Okay, it's a free program. It's available at that website, and that's the details of how to get to that free download. And here's some groups, groups.io, tutorials, and quick start guide in here. And there's another way to get to it a lot faster, and it's this way. And this is Callum. He's got, for instance, here's a modeling for beginners. That's a 5-minute. These are 5-minute YouTube videos. If you go through these videos, you can model your own antennas. Okay, it's that good. It's that simple, and that's how I learned to do this in the last year and a half or so.
Lee, can you do like an off-center fed where you put more length on one side than the other, and then define your impedance and
Sure.
all that?
Yeah.
Can you repeat the question?
Can you? Good point. Can you do an off-center dipole? And the answer is, instead of with the graphical user interface, you just move the connection point where you feed the source, where you attach the source to the wire. And once you do that, you got to remember that changes the impedance. So you got to make a 4-to-1. You got to make it, instead of 50 ohms, you got to change it to 200 ohms. Otherwise, yes, not a problem. Right, right. And an in-fed is an extreme. But the answer is yes, you can do that, and it's fairly straightforward. And the where you do it is pretty obvious in the program. And if you do it a few times, you're going to end up probably doing the same kinds of antennas, so you know the same corners to go after to get the details. But I think you'll be surprised. It's pretty easy. This is an interesting. This guy said one time, all models are wrong, but some are useful. And there's a lot of truth to that. I'll give you an example. Another example. There's a set of models that's never right, but we all use them. Okay, they're good enough. And so you don't have to get 4 decimal points on gain to feel like you got a good model. Oh, here's something I picked up one day. It's an interesting sense of what spectrum's all about. I'll leave it up there. Any questions that we haven't covered? Yes, sir.
Is your presentation available for us to download?
Yeah, it'll be on the website.
Which website?
GAR's website.
Yeah, it'll be on the TechFest website or
Yeah.
ours, and also we'll have this presentation with the video uploaded to our YouTube.
Okay, so okay, good.
And it has the full screen.
Right. You promise? Okay. All right. Anything else? It's fun to work with, and it's not that difficult. And I've learned a lot playing with it, and it's been more fun and more useful, and less frustration than I thought it would be. Yes, sir.
There was, for the free version, there's a limit on the number of points. What's that limit?
I think it's 1,000. I want to say it's either 1 or 10,000. And if you look at the antennas I've modeled so far, there's not many points on it. So it doesn't take a lot. Is that it? Yes, sir.
When you do an off-center fed antenna, the transmission line will now radiate. How do you include that in your model?
My first answer is I don't know. But I think that since you've got a way to split the horizontal and vertical propagation out, that you can see it. You can certainly look at the currents on the elements, including the feed line, and see what you've got. And it's in the propagation pattern.
I guess the easiest solution is never use an off-center fed antenna.
Well, a lot of guys use them for the vertical component part.
Or don't model it.
Well, let's put it this way. Don't use an off-center fed antenna on 15 meters. That one's hard to do. Okay, anything else? Okay. Thank you, folks.